The summation symbols can be put at the start of the formula, and the order or the factor is irrelevant. We can thus, in principle, omit the summation symbols if we make clear in advance over which indices we perform a summation. For instance, in these equations here, we do summation over j from 1 to n of aij vj. You can write that as ijj and imply here that you are summing over the j index. In this slightly more complicated example, you have 3 multiplications, and you're summing over both the j index and the k index in here. So you can write this without the summation symbol and indicate here that you're summing over j and k. Now, when using index notation routinely, one soon experiences that it is unnecessary to denote explicitly over which indices the summation is performed. As you can see here, it can be specified that you're summing over j because the j is repeated. The same case in here, you have that j is repeated in 2 other components and k is also repeated in 2 other components. So these are the indices that are summed, and the index that remains is the index I. So we can introduce the convention, that's the Einstein summation convention, that unless explicitly stated, a summation is assumed over all indices that appear repeated in a product, so the j in here, and no summation is assumed over indices that appear only once. That's the case of the I. So from now on, we'll write all of the formula in index notation with this particular convention, the Einstein summation notation. So in this notation, we have that the dot product, v dot w, becomes vj wj. So the j is repeated, means that these are going to sum over all of the components, x, y, and z. We can use the same thing for the divergence. The divergence is nabla dot w. We can write it as partial j wj, implying that this j here is, again, repeated over x, y, and z. We can also use that for scalars multiplied by vectors. We have here vector v times a scalar phi. That's vi times phi. There is no summation. There is only one. So that's each component of this vector. You can use the same thing for the gradient. Gradient of phi, you can write that as partial I and phi. Again, there is no summation. This is implied that this is true for each component. So partial x, partial y, and partial z. You can use that also for the Laplacian. So the Laplacian of a scalar, Laplacian of phi, that's partial j phi. You're summing the repeated index of j, so that's partial x, so that's partial x squared, partial y, partial y squared, plus partial z squared. And the same thing for vectors. But now in vectors, you see, you have the summation of the j, but then you have one index that is not summed, which is the index of the vector. And then for matrices, you have v dot with a, is vj aij. Notice that this is the same as if you were to write a dot v would be aij vj. And the divergence of a matrix, then we can also define is going to be delta j aij. Notice that the divergence of a matrix is going to drop the dimensionality. You're summing here over the j components. So we're going to have something that has only one index. So that's a vector. So the divergence of a second rank tensor, the divergence of a matrix, returns you a vector. It drops the dimensionality by 1, just like the divergence of a vector drops the dimensionality to a scalar.